Good afternoon. Today we will talk about rigid motions. What is a rigid motion? A rigid motion of Rn is a function f from Rn into Rn that preserves distances, that is the distance of f of p and f of q coincide with the distance between p and q for any pq in Rn. The reason why this notion is important for us is that our goal is to present the fundamental theorem of the curves theory, which says that a curve is essentially uniquely determined by the curvature function and the torsion function up to a rigid motion. This is a result we will present in the next lectures. Okay, now let's consider a special case precisely the case where the rigid motion is linear. Okay, we know very well that a linear transformation of Rn is represented by matrices. So let's introduce some notation. So Mn would be the set of all n times n real matrices, and if A is a matrix in Mn, we define the transformation La from Rn into Rn by the following formula. A multiplied by P, where P is in Rn, and we will suppose that P is a n times 1 column vector because we need to be sure that this matrix multiplication makes sense. Okay, what is now the property that A must satisfies, sorry, in order to be, no, so that LA is a rigid motion. The answer to this question is provided by the following result. It's proposition 1.55, which says that the following statements are equivalent. The following statements are equivalent. So now I will present a list of 6 statements, and then I will prove they are equivalent in the following order. I will prove that 1 is equivalent to 2. I will prove that 2 is equivalent to 3. I will prove that 3 implies 4. 4 implies 5. 5 is equivalent to 6. And 5 implies 3. So this is a scheme of the proof. So what is the statement number 1? The first one is LA is a rigid motion. And what is the statement number 2? Number 2 is the following: A is orthogonal. What does it mean to be orthogonal? It means that the length of AP is equal to the length of P for any P in Rn. And probably you already know that On denotes the set of all orthogonal matrices in Mn. Okay, let's prove that 1 is equivalent to 2 instead of giving the other 4 statements. This way we will save time. So proof of the equivalence between 1 and 2. So if LA is a rigid motion, then LA preserves distances. So I can write what follows. Length of LA P. This can be written as LA P minus LA of 0. This is clear because LA is linear, so this is 0, the 0 vector. Now I use the fact that LA is a rigid motion, so the length of LAP minus LA is 0. That is the distance between LAP and LA 0 is equal to the distance between P and 0, that in this new notation is P minus 0, but this is the length of P. So we proved that the length of LAP coincides with the length of P, which is exactly the condition you have here. So this says that A is orthogonal. Now, conversely, if A is orthogonal, I have to prove that LA is a rigid motion. So I have to prove that LA the distance between LAP and LAQ that I can write as LAP minus LAQ is equal to P minus Q. So this is the equality I have to prove, but this is clear. Why? Because this, by linearity, can be written as the length of LAP minus Q, and by the orthogonality of A, this coincides with the length of P minus Q. So this is equal to this. So implies LA is a rigid motion. So now, what are the properties of linear rigid motions? The answer to this question is provided by the other statements of the proposition. So the first one is number 3, and it says that the inner product of LAP with LAQ, this coincides with the inner product of P and Q for any PQ in Rn. This property can be reformulated as follows. That is LA preserves the inner product. Okay, now let's prove that 2 is equivalent to 3. So I have to prove that if that A orthogonal is equivalent to this property here. Okay, suppose that 3 holds true, then you have that LAP multiplied by LAQ, this is equal to P multiplied by Q. But we can take the square root of both sides. Excuse me, I made a typo. I have to take the inner product of LAP with itself. And what do we have on the right hand side? This is the length of P, and what we have on the left hand side, this is the length of LAP. So we prove that once again the length of LAP is equal to the length of P, and this means that A is orthogonal. So this implies A is orthogonal. Now let's prove the converse. Conversely, if A is orthogonal, we want to prove that LA preserves the inner product. Okay, the idea is show first that the inner product is completely determined by the norm. What is the meaning of this sentence? It means that the inner product of two vectors in Rn can be written in terms of the norms of P and Q and the norm of the difference. Precisely, the following formula holds true. We have 1/2 length of P squared plus length of Q squared minus P minus Q squared. What is a norm is the length, what we call length of P. So here you have the square of the norm of P, or equivalently the square of the length of P. Here you have the square of the norm of Q, and here you have the square of the norm of P minus Q. How can you prove this formula? This formula can be proved writing down the expansion for P minus Q length squared and solve the identity you get for the inner product of P and Q, and you will get this formula. Okay, now we want to use this formula for proving that if A is orthogonal, then LA preserves the inner product, but this is immediate. So LA preserves the inner product because essentially LA preserves norms. But this is true because LA P in length is equal to the length of P. So in other terms, let's call this the right hand side of this equation star. Then star is equal to 1/2 LA P in length squared because of this formula, plus length of LA Q squared. I use once again this formula with the P replaced by Q, minus length of LA P minus Q squared. I use once again this formula with P minus Q instead of P. And what is this? This is the inner product of LAP by LAQ. Why this is true? I am using this formula where P has been replaced by LAP, Q has been replaced by LAQ, and P minus Q has been replaced by LAP minus Q. Okay, so this proves that LA preserves inner products. Why? Because this one is equal to star, but star is equal to this one. So this is P Q. Okay, now we have to prove the equivalence with 4, where 4 is LA preserves orthonormal basis. That is, if P1, P2, Pn is an orthonormal basis over N, is an orthonormal basis over N, then so is LA P1, LA P2, LA Pn. So as announced before, I'm going to prove 3 implies 4. So I have to prove that if LA preserves inner products, then LA preserves orthonormal basis. This is trivial. Why? the condition that LA preserves orthonormal basis, the condition that LA preserves inner products says that LAP multiplied by LAQ is equal to the inner product of P and Q. So this implies that LAPI multiplied by LAPJ is equal to PI comma PJ. So you get that if I is equal to J, LAPI, LAPI, this is 1, because this is PI comma PI, and if I is different from J, you get that LAPI comma LAPJ, this is 0, because this is PI comma PJ. Because by hypothesis, P1, P2, P3, Pn is an orthonormal basis. So 4 is proved. So I should write that is LA P1, LA P2, LA Pn is an orthonormal basis. Okay, let's pass to the statement number 5. 5 says the columns of A form an orthonormal basis over N. And I will prove that 4 implies 5. The reason why this is true is that the columns of A are LAE1, LAE2, LAEN, where E1, E2, En is the standard orthonormal basis over N. And now we use the fact that the 4 says that LA, so by 4, LA preserves orthonormal basis. So in other terms, if this is an orthonormal basis, then also this one will be an orthonormal basis. Okay, let's pass to the statement number 6. Six says that A transpose multiplied by A is the identity. Okay, why this is true? So we will prove that 5 is equivalent, sorry, I made a mistake. Proof of 5 equivalent to 6. What is the ij entry of the matrix A transpose A? How do you multiply, how do you find the ij entry of a product? Very easy. This is the inner product of the ith row of A transpose, and you multiply it by the jth column of A. So this is follows from the definition of product. I did nothing. And now we use the definition of transpose. What is the ith row of A transpose? This is the ith column of A, and I multiply it by the jth column of A. But the column of A are this vector here, LA E1, LA E2, LA E3, LA AN. And this is an orthonormal basis. So this means that this is equal to 1. Let's write here. This is equal to 1 if I is equal to j, and 0 if I is different from j. So this implies that A transpose A transpose A is I. Now it remains to prove that 5 implies 3. So essentially 5 is, so I will call it here, 5 is the columns of A form an orthonormal basis, and 3 is LA preserves the inner product. So LA of P multiplied by LA of Q, this is equal to the inner product on P and Q. So how to show that 5 implies 3? Now, okay, suppose that P is the vector component P1, P2, Pn, and Q is the vector of components Q1, Q2, Qn. In other terms, P is equal to sum on L of PL EL, and Q is the sum on S of QS ES. So what is then LAP multiplied by LNQ? This is LA of sum on L of PL EL multiplied by LA. Oh, sorry, I don't have space, so let's maybe try to write smaller. Sum on S of QS, yes. No. This is an inner product, so I have to write this way. So by linearity, this is equal to the inner product of LA EL, LA ES, and in front of it we have a sum on L and S of PLQS. But we know very well who are these two terms. This is the Lth column of A, and this is the Sth column of A. And by hypothesis, they are are two elements of the orthonormal basis of Rn. So this means that if L is equal to S, you get 1. And if L is different from S, you get 0. So I can write that this sum is sum on Ls of PL QS delta Ls, where delta Ls is a symbol which is 1 or 0 according to the fact that L is equal to S or L is different from S. So this is sum of P LQL on L, that is the inner product of P and Q. So we proved that this inner product is equal to this inner product, and it is done. So we proved that LA preserves inner products. Okay. Next goal is the characterization of rigid motions which fix the origin. In other terms, we want to answer the following questions. How a rigid motion which fixes the origin looks like. The answer to this question is provided by proposition 1.57, which says that if F is a rigid motion which fixes the origin, that is f of 0 is 0, then f is equal to LA with A in ON. In particular, this implies also that F is linear because LA is a linear transformation. Okay, let's prove this. The proof is based on an identity we already used a few minutes ago. And I will rewrite here. So before I use that PQ, inner product of PQ is 1/2 length of P squared plus length of Q squared minus P minus Q length squared. And now I rewrite this changing the notation. So this is 1/2 times distance between P and 0 squared plus the distance between Q and 0 squared minus the distance of P minus Q and 0 squared. Now, by hypothesis, F is a rigid motion, so F preserves distances, and this implies that this quantity is equal to 1/2 distance of F of P 0 squared plus the distance of F of Q 0 squared minus the distance of P minus Q, F of P minus Q and 0 squared sorry, I wrote something which is not correct, so I can write the length of the square of P minus Q also this way, but in order to prove my result, it's more convenient to write this way. So the length of P minus Q squared is the distance between P and Q. So here I will have that this term is equal to this term. Also, before it was correct, but I cannot continue because I don't know so far that f is linear. Okay, now let's observe what do we have on the blackboard. On the blackboard we have the inner product of f of p and f of q. So we proved that f preserves the inner product. Why? Because I proved that this inner product is equal to this one. Okay, now let's introduce a matrix. Let A be the matrix whose ith column is f of A. Sorry, f of EA. So in other terms, f of EI equals to LA EI. We have to prove two things. We have to prove one, that A is orthogonal, two, that F is LA. Okay, why one is true? One holds true because the column of A form an orthonormal basis, so these are orthogonal. In order to prove 2, in order to prove 2, we use the following idea. We will show that the transformation defined by G equal LA inverse composite F is the identity. Okay, so G is a rigid motion. Why? Because G is the composition of two rigid motions. And also we have that G of 0 is 0. And this implies G preserves norms and distances and inner products. And we have also G of EI equal to EI by definition of LA. So let P the sum on I of AI of EI, and GP equal sum on I, no, it's change index, no, I can use the same, of BI, EI. My goal is to show that BI is equal to AI implies G of P equal P. That is, G is the identity function. Okay, this is very easy to do. So what is BI? BI can be obtained from this formula, multiplying both sides by EI. So BI is GP EI equals sum of, no, sorry, I forgot something. This is GP of GEI, but G preserves inner products, so this is PEI, but P is here, so what is PEI? Is the sum, is the inner product of the sum of AI, EI with EI, so this is AI. So we prove that the BI coincides with AI. Okay. Next goal is the characterization of rigid motions which do not fix the origin, which do not fix the origin. The answer is provided by proposition 1.58, which says that if F is a rigid motion, F is a rigid motion, of Rn, then we have this formula: F is equal to TQ composed with LA, where TQ denotes the translation a map defined by TPQ equal, TQP equal P plus Q for any P in Rn, and we have also the fact that this composition is unique. That is, Q in Rn and A in On are unique. Okay, how to prove this? Set Q equal F of 0. Then TQ inverse composed with F is a rigid motion Why? Because TQ inverse is a translation, and translations are rigid motions because they preserve distances, and composition of rigid motions is a rigid motion. This rigid motion is special for the following reason. You have that TQ inverse composed with F applied to 0. This is TQ inverse of F of 0, which is Q, and this is 0. So this is a rigid motion which fixes the origin. That is, it fixes the origin. Then we can use the result presented a few minutes ago. TQ inverse composed with F is LA with some A in On. And this implies that if you compose both sides by TQ, you get that F is equal to TQ composed with LA. So now we have to prove only that the decomposition is unique. So suppose it is not true. Suppose there exists a Q bar in Rn and A bar in On. No, maybe let's use a different notation. No, it's okay. Such that F is a TQ bar composed with LA bar. Okay, then TQ composed with LA is equal to TQ bar composed with LA bar. Then if we compose, for example, both sides with the inverse of TQ bar, we get TQ bar inverse composed with TQ composed with LA equal LA bar. Okay, now let's compose both sides on the right with the inverse of LA. So we get the TQ bar inverse composed with TQ equal to LA bar composed with LA inverse. Okay, so on the left we have a translation. In fact, TQ bar inverse is T minus Q bar. So this means that the translation T minus Q bar composed with TQ, it is nothing but then T composed with, is a T of minus Q bar plus Q. So this is a translation. Instead, on the right, we have a transformation which fixes the origin. Why? Because LA fixes the origin, so its inverse fixes the origin. LA bar fixes the origin, and this composition will fix the origin. So also this one must fix the origin. Because this transformation must coincide with this. So this implies that minus Q bar plus Q must be 0. That is Q equal Q bar. So we proved that T minus Q bar plus Q reduces to T0, that is identity. The identity function. So maybe let's write it as this way, identity. So the identity function must coincide also with this transformation here. LA composed with the inverse of LA. What is LA inverse? If LA is defined by AP. It is clear that LA inverse of Q is A inverse of Q. Think a moment and you will convince yourself that this is true. Now, LA inverse, so LA bar is LA inverse, and this implies that LA bar composed with LA, no, sorry, I made a typo. I mean LA inverse is LA bar, LA inverse. So LA bar of LA inverse, this is LA bar composed with LA inverse. And this is the map defined by this formula. This is A bar multiplied by A inverse P. Of course, A inverse exists because A is orthogonal. And this is L of A bar A inverse P. So the conclusion is that LA bar composed with LA inverse is L A bar A inverse. So we started from here. Identity equal to LA bar composed with LA inverse. This is equivalent to identity equal to L A bar A inverse. This identity is possible only A bar is A. So we proved that the decomposition is unique. Okay, let me check how much time I have. Okay, approximately 10 minutes. Now let's talk about the orientation of orthonormal bases. Definition 1.62. An ordered orthonormal basis V1, V2, Vn over n is positively oriented if the matrix, the orthogonal matrix, that you get writing the vector of the basis as a column matrices has a determinant one, and is negatively oriented if it has determinant minus 1. Now let's see what happens if we consider oriented bases in R2 and R3. So in R2, the ordered orthonormal basis V1, V2 is positively oriented if V2 is R90 V1. Do you remember what is R90? R90 is a counterclockwise rotation by 90 degrees. And negatively oriented if V2 is minus R90 V1. Why this is true? V1, V2 are unit length vectors, and they are orthogonal. So if V1 is a cosinus of theta, sinus of theta for some theta, then there are only two options for V2. This one or this one. So in this case, V2 is given by minus sinus of theta cosinus theta. You can make a simple computation to show this. You have to find V2 in order to be orthogonal to V1 and of length 1. Or this one. And in this case, the matrix will be cosinus of theta, sinus of theta. The opposite of this vector is sinus of theta minus cosinus of theta. So it's now immediate to say that V2 in this case is R90 V1, and in this other case V2 is minus R90 V1. Why? Because R90 of the vector component xy is minus yx. What about R3? The ordered orthonormal basis V1, V2, V3 is positively oriented or right-handed, if V3 is the cross product of V1 and V2. And it is negatively oriented if V3 is minus V1 times V2, that is V2 cross V1. So example, there is an ordered orthonormal basis that we know very well. Is a vector T of T and of T B of T, the Frenet frame. We know that B of T has been defined as the cross product of T and N, so implies it is always positively oriented. Okay, so if you want to prove this result, just write down the formula for V3 and prove that the determinant of the matrix whose columns are V1, V2, V3 is positive and equal to +1 in this case, and -1 in this other case. Okay, that's all for today. Thank you for your attention.